So our next speaker is actually our keynote talk. Professor Koki of the Georgia Institute of Technology, formerly of the University of Illinois and JPL. He also earned his PhD at MIT and a bachelor and master from the University of Tokyo, a great university. He has received numerous awards, including the NSF Career Award, NASA Early Career Faculty Award, and DARPA Young Faculty. And actually, he currently serves as the chair of the AIAA Space Logistics Technical Committee. So Professor Koki is a top expert, and we're lucky to have him. Let's see, maybe he doesn't have permission to speak yet. That'd be a good step. Here we are.
Okay, so you can hear me now?
Yes, thank you very much, Professor Ho.
Okay, yeah, thank you very much for inviting me, and thank you for providing me with this opportunity to talk with this many people, including some people that I know from before, and many new folks as well. So let me share my screen so that I can show my presentation. This is not the screen that I was intending to share. Just a second. Okay. Okay, so hopefully you can see my slide. So my name is Koki. Thank you for the introduction. I'm currently the assistant professor of aerospace engineering and the director of the Space System Optimization Group at Georgia Institute of Technology, or Georgia Tech. So today I want to talk about space logistics modeling and optimization for space exploration and on-orbit servicing. I will go over a variety of different domains where space logistics can be useful and can be effective, can really transform the way we design space missions. And I will not dive into each of the topic in very detail because I want to cover different domains for space logistics. But I have the papers that we have published at the bottom for your reference. If you're interested in, please feel free to, of course, read these papers. Or if you don't have access to that, just send me an email. I'm happy to help. Or I'm happy to have more discussions if needed. So I direct the Space System Optimization Group at Georgia Tech. Our mission is to create optimization models and methods to tackle complex space mission design and system engineering challenges. Particularly, what we're trying to do is to explore the role of optimization in the space mission design to hopefully replace some of the qualitative or manual process by some automated optimization. You'll see what I mean later on. And more relevant to this particular workshop, we're trying to pioneer some of the logistics-driven modeling and optimization method in the space mission design. And we have those domains that I will be talking about. One is about campaign-level space exploration mission design. And the second is on-orbit servicing, assembly, manufacturing, the topic you probably are already familiar with after this, the past few hours of presentation. And then the third one is about mega scale small-sat constellations. So before I jump into each of these domains, I want to just define the space logistics. So what do we mean by space logistics? How is it different from just space engineering that we typically refer to? We actually have a formal definition of space logistics defined by AIAA Space Logistics Technical Committee, for which I'm the chair since 2017. So our definition, so this is we have been regularly updating this definition. This is the most up-to-date definition. Space logistics, we define it as the theory and practice of driving space system design for operability and supportability, and of managing the flow of material, services, information needed throughout the space system lifecycle. So there are a few keywords here. One is that this is about management of the flow of material, service, and information. So we are not looking at each mission, right, separately. We are looking at the flow of materials, services, information that govern the space mission. And also another keyword is that we're looking at the space system lifecycle. So we're not just looking at one particular instance of a space system operation. We're looking at the life cycle of a space system. So those are some of the keywords that is behind the space logistics. So from here, I want to talk about each of the three domains I showed earlier and how space logistics approach, space logistics modeling optimization approach can really help resolve some of the challenges for those domains. So the first domain I want to talk about is about space exploration, or particularly the campaign level space exploration or multi-mission space exploration. So if you look at the past or current space exploration like Apollo or ISS, their logistics paradigm belong to, for example, carry along or resupply strategy. So Apollo was carry along, where you carry everything you need for each mission to the destination. And ISS more like a resupply. You have the ISS up there, you send your vehicle to resupply consumables or even replace the crew. However, when you think about the future space exploration, where you have multiple destinations, multiple origins, and multiple missions coordinated with each other, the pure carry along or resupply would not work effectively. Instead, we may need a new logistics paradigm, which can be a combination of a pre-positioning, carry along, and resupply. And it can also involve the efficient use of space logistics infrastructure, such as in situ resource utilization or ISRU and propellant depot. So as probably many of you are familiar with, so ISRU is like oil field in space. It's like space mining, right? You can generate the resource from the in situ environment, like propellant, water, life support gas from the lunar surface or Martian surface. But ISRU has its own limitation in that you need a large cost to pre-deploy, and of course the plant mass is not negligible, and also it involves a lot of developmental costs. And propellant depot, on the other hand, is like a gas station in orbit. It stores a propellant structure in space, and it can be at Lagrangian points, it can be at Earth orbit, but the caveat of using propellant depot is that it needs to be refilled by the tankers frequently, right, from the Earth or from ISRU. And if you store propellant at ISRU for a long time, it has a boil off. So the key question here from a logistics perspective is how we want to use this infrastructure. Are they actually useful? Are they actually effective or efficient considering the entire campaign, entire life cycle, right? And including the deployment of this infrastructure and also utilization of this. And by the way, the boundary between deployment and utilization may not be as clear as it could be. Like ISS, we have been, started operation for a long time before it became it's fully assembled, right? So the deployment, you can operate it at the same time as deploying them. And so these are the questions that is very important to address. You can't just look at ISRU and say, oh, ISRU is useful because it can provide this much resource. Instead, you need to look at the entire logistics program. Right? How much does it cost? Like how long does it take to generate those resources? Right? Those questions need to be all considered. So there are a lot of different ways to tackle this problem. And from logistics perspective, we believe this is the most efficient way, which is based on the network. So basically, we consider this space exploration problem as a logistics problem. It's like what FedEx or Amazon does when they design their logistics system. We consider the entire space exploration as like a subway map. Each orbit corresponds to each node, and we connect them with arcs. So we have a space exploration as a network problem, and we have a multi-commodity flow. We have multiple commodities flowing over them. The commodity can include payload, vehicle, propellant, food, and so on, right? Even the crew themselves. So this way, we can formulate this problem in an efficient way, so that it can solve in a similar way as how the terrestrial large-scale logistics problem are solved. Now, this is not it, right? Mission planning, this network planning is not the entire problem. We still have other problems like spacecraft design, right? We need to, unlike the terrestrial logistics problem, for space, we are also designing the spacecraft, particularly for some missions or for some campaigns. So spacecraft design is part of the trade space that need to be considered together with mission planning. And infrastructure design, like ISRU design, is of course also part of the problem. What is the size of ISRU? What are the design we want to apply for each subsystem of ISRU, like power, storage, excavation system, and so on? All these are part of the problem we need to tackle. And so getting inspiration from the logistics approach used for the terrestrial applications, we have developed a new method, which is published in the paper that is referenced in the bottom in 2018. So in this one, we developed an efficient method that can optimize basically everything together. It can optimize the commodity transportation flow for different commodities like payload, propellant, consumables, and the sizing of spacecraft and mission timeline sequence. Everything can be optimized. And the approach we took is, I will not get into this in detail, but this is called dynamic generalized multi-community flow. This was originally developed by some other folks. The original form for the static form was developed by Takuto Ishimatsu. And then in my PhD, I developed a new formulation of that to extend it in the dynamic direction in a more efficient way so that it can actually be used for mission planning. Before it was more for the static design. Now we are looking at the time series mission planning. And then after that, we have added more details in it so that we can consider more higher fidelity spacecraft design and ISRU design, even at the subsystem level. So basically you consider the network, right? You consider the nodes and arcs. And at each node, we have mass balance. And at each arcs, we have a flow transformation. And there are a lot of details behind it. I'll let you read the papers if you're interested in it. But I just want to stop here for this one. So I want to share some results, right? What it can do. So for this problem, this is a case study for the Lunar campaign. We tell the optimizer that we want to go to the moon 3 times, right? We have the particular demands for each of these missions. We want to, send in this case 40 to 100 kilogram of equipment or payload at every mission, and then we need to send human to the moon, a particular number of crew. I think it was 12 for this case. So that's the information we give to the optimizer, and we let the optimizer to decide to optimize the entire mission sequence that is shown here. So the optimizer will first size the spacecraft. So it will tell you what is the size of the spacecraft. In this case, we have 2 types of stages, the bigger one, smaller one. The detailed size, like what is the propellant, what is the capacity for the payload and or the structure mass, and everything is sized by the optimizer. So this is size the stage, and it will optimize how we want to use those stages. It will tell you, say, here we use this 4th stage, and we leave 1 stage in low lunar orbit. And then we send the remaining stage to the lunar surface, and then we use a small stage to take the crew back. And then some stage will keep staying there. They can be used as a propellant depot. Like everything is found by the optimizer. And also the optimizer in this case determined that ISRU is actually more effective. And so they decided to use ISRU. They will size ISRU optimally. So in this case, 1400 kilogram is ISRU planned that the optimizer decide to send. Think this is optimal size. And this ISRU, of course, will generate propellant, and it will be used later on in the 2nd or 3rd mission. So this entire sequence, entire multi-mission, the key is that multi-mission. We're not considering each mission separately. This is a multi-mission design, and this entire sequence, the computation only takes 5 minutes. So this optimization problem, the tool can really be an effective decision support tool for automated space campaign analysis design, considering the deployment and utilization of the infrastructure element. And again, the key is that here we are leveraging the logistics-driven approach, right? We are viewing the problem not just as a trajectory design problem or orbit design problem. We're viewing the problem as a logistics problem, commodity flow problem, and use approach based on that terrestrial logistics, inspired by the terrestrial logistics design. So that's how space logistics can be very powerful. So that's one, the first domain. And the second domain I want to talk about is about on-orbit servicing, assembly, manufacturing. So I'm sure you're already familiar with the concept. So maintenance is a phase that's often missing, right, in the traditional space missions. So the spacecraft, once you launch it, it's hard to provide additional fuel or repair or even deorbit. So on-orbit servicing is really the key, and assembly manufacturing is also the additional steps that are needed. So this on-orbit servicing, if you think about the long term, right, what we want to do eventually for on-orbit servicing, most likely we are not just sending one servicer to go that is dedicated for servicing for a particular spacecraft, like what we did for the Hubble Space Telescope. Instead, we probably want to have some infrastructure, right? In for example, geosynchronous orbit, which has some depot for the spares, right? Those are the spares depot. And then you have a servicer that will leave the depot to go to the satellite and provide service and come back. And because it's an infrastructure, you want to provide a responsive service, right? So you don't know when the failure will happen. You don't know where the failure will happen, but you want to provide a responsive service using your infrastructure. That's kind of the, I think that's kind of the end goal that we want to achieve in on-orbit servicing. Now, this problem becomes way more complex than just design and routing of a particular vehicle, right? You need to consider the entire commodity flow of the spares. You need to consider how responsive this problem is under the uncertainty in the failure, uncertainty in the service time, uncertainty in the launch schedule. So everything is uncertain, stochastic. How do we consider this problem? Again, the inspiration comes from how the terrestrial logistics have been tackled. When you think about a fire station, for example, right? It's very similar. You don't know where the fire will happen. You don't know when the next fire will happen, but you want to design your fire station system so that you can provide the responsive service. And one approach would be use agent-based simulations. That is kind of a classical approach. You just simulate it for a long time, many instances. Hopefully you have some solution converge at some point, but it takes very long time, hours, or maybe even tens of hours or days. And we have looked into this problem and see whether we have a better approach. So we came up with a semi-analytical model, which is based on the spatial queuing theory. So queuing theory is basically a theory that has been used for example, design an ATM system or design the firefighting station, where you have a probabilistic service rate, you have a probabilistic arrival rate or failure rate in this case, and you can evaluate how long it takes, how responsive the service would be. And we also have the inventory management problem, because this is different from just a fire station, because we are also dealing with the inventory of the spares. We want to make sure that we have sufficient spares of the in stock when needed, right, in your spare depot. So this is a more complex problem than firefighting station. But so we developed this semi-analytical method, which has this spatial queuing theory and inventory management coupled. So it's quite mathematically involved, but it's a very interesting model. And as a result, we can now cut down the analysis time to seconds. So we are cutting down from hours to seconds. So that's pretty powerful. Again, thanks to the inspiration from the terrestrial logistics problem. And this is just a result to show how accurate we can reach. So this black line is a simulation. Each black dot is a simulation instances. As you can see, when the depot capacity, oh, by the way, yeah, this y-axis is the mean waiting time, which is basically the performance, how responsive you are. X-axis is the depot capacity, which is a cost, right? The bigger the capacity, of course, the better the performance, but you also have a lot of station keeping, propellant, and cost, and so on. So this is a classical trade-off between performance and the cost. And you can see that our semi-analytical model approximates the simulation results pretty well, at least the mean value pretty well. So this can be used for a large-scale trace-based exploration, because each of these cases only takes seconds. And the bigger the capacity, the higher the reliability. And in reality, we are looking for a higher reliability case. So this area, like from the 15 to 25, is the area that we actually are interested in. And as you can see, the semi-analytical model is very accurate. And there are many details in many more details behind this. So this paper at the bottom is our recent paper on this topic. If you're interested in, feel free to refer to this. And we have to go a little bit beyond this. By the way, the previous one was DARPA project. This is also part of the DARPA project. So can we combine this, network problem we looked at earlier to this on-orbit servicing? Because most likely we want to design the mission sequence for the on-orbit servicing as well. And it was successful. We did that. And so now we have an optimizer that can optimize the vehicles, not only the vehicles, but also the fuel, spares, tools, materials, all the commodities that flow over this network. So this is not beyond just vehicle routing, like a driving sales problem. It captures the entire logistics commodity flow. And they can consider both high thrust and low thrust, and they can consider both the short term and the long term using the rolling horizon and considering the uncertainty in the demand. So this paper was just accepted. It hasn't been published online yet. It should be very soon, but I'm happy to share the manuscript if you're interested in this work. The references at the bottom. So with the remaining, probably not very long time, I want to talk about the third domain, which is satellite constellation. This is another very interesting domain. We have a recent trend of mega constellation, hundreds of thousands of satellites proposed by SpaceX, Amazon, OneWeb, which unfortunately had bankrupted. But we believe that there's some hidden challenges in this mega constellation. This is a scale that we have never dealt with in the past. And it's not straightforward. It's not just using the small scale constellation and just use the same approach for the bigger scale by increasing the number of satellites. It's not that easy. There are some hidden challenges behind it. And some of the challenges come from the deployment. How do we deploy that many satellites all at once? Probably not possible. So how do we deploy them in stages? How do we do the maintenance for this? And how to manage the debris caused by these constellations? I will talk about two of our research that tackle this scalability challenge. One is about maintenance. So when you think about maintenance basically meaning that the satellite may fail, right? Especially when we're talking about a small satellite, the lifespan usually is shorter than the large, big satellite. So when you think about this mega constellation with a bunch of small satellites, hundreds, thousands of small satellites, the traditional spare strategy will be have some additional spare satellite in each orbital plane. But that will end up being many satellites if you want to make sure the service is continuous or reliable. Because the number of satellites are many, so the failure also happens pretty frequently. So you need to have a lot of spare satellites in orbit. And that's not very efficient. So can we do better than that? So one approach to have is to have some parking orbit at a little bit lower altitude, and then you have some spares in plane as well to provide continuous service whenever something fails, and then you have some satellites in the parking orbit that can replenish the in-orbit in-plane service, in-plane spares, and then we have some ground spares that can replenish the parking orbit spares whenever it runs out. So that concept itself has been around, but how do we optimize it? This is actually not easy to analyze, right? Because how many parking orbits do you need, right? You probably need multiple planes, right? Because you have many planes in the actual constellation, but how many do you need? And how many spares do you want to allocate, right? To the constellation plane, to the parking orbit, to the ground, and and how do we, decide when to deliver some spares from one orbit to another orbit? That itself becomes very complex. Again, the traditional approach will be used simulation. It takes a very long time, not necessarily repeatable, and it's useful for high fidelity validation, but not useful for a large scale trace-based exploration or optimization in the initial stage. So again, the inspiration comes from terrestrial logistics. So we developed a model based on the multi-echelon inventory management, which is kind of a very interesting model, analytical. This is fully analytical model designed for the logistics relationship between the warehouse and the manufacturer and the retailer. So in this case, ground is a manufacturer, and the parking orbits are the warehouse, and each constellation plane corresponds to the retailer. So and the transportation between each of these orbits, of course, is governed by the orbital dynamics, and also in this case, we are leveraging the J2 perturbation to wait until the plane align with each other. And then the lead time between the ground and parking orbit depends on the launch opportunity, which is also stochastic. So we developed this new model that can incorporate all these orbital dynamics using multi-echelon inventory approach. And it ended up being, again, a fully analytical, very efficient model to analyze, considering all these probabilistic uncertainties to analyze the performance. And using this model, which is very efficient, we can run large-scale optimization to find how many spares we have and what is the inventory management control policy to decide when to deliver one spare from one place to another place. Everything can be optimized very efficiently, even for mega constellation, like with hundreds or thousands of satellites. So that's again very powerful way the logistics can be leveraged. The paper is at the bottom. We have published in 2019. And this is the last topic I want to talk about, which is about the deployment. So when you think about a mega constellation with hundreds of satellites, you can't launch all of them at the same time. You have to launch them in stages. So one strategy will be to consider the global coverage, right? You just send satellites to satisfy the global coverage, and you send more and more and more so that it's populated in the Walker Delta constellation pattern, for example. But that's not necessarily the best strategy, because there are some area that has a higher demand, like Japan or the United States or Europe, that has a concentrated area of high demand. And there are other areas which has almost no demand, right? Like Pacific Oceans. There are demand, but the demand is relatively small. Now, eventually you want to provide global coverage, but is it really a good strategy to start from the global coverage with a very thin layer of constellation, or is it better to start from the regional coverage that is dedicated for some particular highly concentrated demand concentrated area? So the latter is what we propose. So we compare this analysis, this case, with a global case. And this case has its own benefit, and it can be more efficient under certain scenario. So we consider that the area of interest can change, right? Now the area of interest is Japan, maybe. Next, it can be Europe, it can be India, it can be the US. So we can, consider all this flexibility, right, by designing our regional constellation that has a built-in, what we call built-in flexibility. So this becomes a stochastic optimization problem, very interesting problem. And also we develop a new efficient way to optimize this regional coverage using a circular conversion theory. So it turns out that we can optimize this regional coverage very efficiently. We can incorporate that into this stage deployment optimization and the uncertain area of interest. And the result is very interesting. Again, we have published 2 papers on this. One is focusing on this stage deployment. The other is focusing on the optimizing of this regional coverage. And feel free to refer to those papers. So this is kind of another challenge where the logistics will come in and help resolve. So I think the key message I want to convey here is that space logistics modeling and optimization is becoming more and more impactful, because the space exploration, space systems have become more and more complex, and we have more and more challenges in this scalability, or how do we consider this such a complex system, and how do we consider such a campaign that has multiple missions interacting with each other? How do we leverage those logistics ideas? So the examples I have showed are driven by the logistics, meaning how, again, FedEx, Amazon, Apple, all these companies have been doing that. We have a lot of approach that have been developed for logistics on the ground. But we need modification with orbital mechanics, with a lot of new challenges that exist in space exploration. And that's where the research question is. And I'm very proud to be a pioneer in this field, and I hope that many of you can join us to really open this new field together and tackle a lot of challenges that exist in the future space exploration. So in the end, I want to acknowledge my fantastic grad students and many more undergrad students. There are too many names that can fit in this slide, and also the sponsor, including the NASA, DARPA, NSF, and so on. So thank you very much. I am happy to take any questions right now. I have to leave after this because my other commitment, but I'm happy to answer any questions right now.
Thank you very much, Professor Koki. It was most interesting. We do have some questions in our chat.
Yes.
Maybe we can start with it and then continue with questions from audience. Well, the question from Marc Andre. there was graph visualization of the space logistics network, and it was very interesting. How might the visualization change for electric propulsion?
Yes, so electric propulsion is very interesting in different perspective. So one of them is that so there are a lot of different types of electric propulsion. For example, when you can consider a constant thrust state, right? You have a SEP state, a solar electric propulsion state that has a constant thrust. Then what's interesting here is that whenever you have a payload, right, your acceleration will change depending on your payload, right? Because your thrust is constant. So if you have a big payload, your acceleration is slow. If you have a slow payload, a small payload, the acceleration will be big. So this actually makes the problem more interesting and more challenging because depending on your payload, your trajectory will change, your time of flight will change, your delta V or your propellant usage will change. And we have another paper which is not referred here. So this paper was published last year that particularly looked into this problem. We developed a new way to solve this using event-driven network modeling. Here we basically consider this electric propulsion as a separate trajectory problem, and we can model this trajectory using a kind of surrogate model and put that into this logistics paradigm. And this worked out very well. So there are approaches to consider electric propulsion, but it's not the particular way that I showed here, but the similar approach can be applied. And that's a great question. Thank you.
Yeah, thank you for the answer. Maybe some other questions from the audience. It's about spare parts management. Well, the question from Marc-André. In spare parts management, he thinks depot placement is a key question. What about in this case? What are the parts warehouses?
So parts warehouse in this case is like a spare depot that is in a particular slot in geosynchronous orbit. So you can consider, so in this case, we're dealing with the geosynchronous orbit servicing, which is a case that DARPA is interested in. So we have basically a depot that has a certain capacity. So you can only store the depot up to a certain capacity. Sorry, you can only spare the number of spares. You can only store the spares up to a certain capacity. And then whenever needed, the servicer will pick a spare from that depot and then go to the satellite and fix it and comes back. So the depot is a separate infrastructure element that is needed at a particular slot. And the optimization of the location of that depot is also an interesting optimization problem. Or the question whether you want multiple depot or just one, or that's also an interesting trade-off.
Yeah, thank you.